Yeah, ma'am. Sure. Not an issue,
So
not an issue.
Anudeep is helping me in recording, so he's also here.
Mm-hmm.
Okay.
Okay, ma'am. You are live on YouTube.
Really?
Yes.
Wow. So I should be very careful.
No, there is something else. It's something else. I'm not sure.
What was I saying? Live on YouTube and
On top right corner, you can say it's live, written live. So I
yeah,
was,
yeah, yeah, it's live and it's being recorded also.
yeah, yeah, okay, okay.
What should be the agenda? Week wise. Yes, yes. Week wise, we are discussing the topics, and for each algorithm, we'll do one problem.
Okay, ma'am.
That's what I'm planning. If there are still unsolved questions, we can take that. I'll try to keep this simple.
Yeah, sure, ma'am, sure.
Okay, maybe we can start, right? I think my screen is visible.
Yeah, it's visible.
Yeah, so the basic disclaimer is I'm just learning, just like all of you. I'm sharing my way of understanding the concepts. So correct me if I go wrong anywhere, and please feel free to put forward your ways of doing things also. Okay. So let's start. I have this document which guides me in this taking this session forward. Earlier, the quick recap is that we have in our previous weeks we have this algorithms of search: DFS, BFS, and DFID. These three come under uninformed, means they don't have the idea of where the goal is, and they can still find out an optimal path. Each algorithm has its own disadvantages. DFS is simple, but it is not good for infinite depth problems, and BFS, it will give a solution with least number of moves, but when the edge cost is associated, it will not consider that, and it will not perform accordingly. Also, it has high branching factor. And then we saw DFID, which has depth bounds are iteratively increased, but the issue was that it is re-exploring all the nodes every time. So basically, for all this, the biggest issue is that they are not guided towards the goal. So there was a need to check for guided algorithms, which were best first and hill climbing. But unfortunately, in both of these, we lost this opportunity to find the optimal solution. Best first was prioritizing good new nodes using heuristic. It means whatever nodes are what to say nearer to the goal, it was prioritizing them. But in that case, somehow if the heuristic is bad, or the estimations are bad, it will not give shortest paths. Hill climbing, as we all know, it moves to better neighbors, but it can possibly stuck on a local minimum. So both these are guided, but we lost this optimal solution finding. So from week 5, we are moving to better algorithms which are both guided and which are guaranteed to give optimal solutions under some conditions. So the first one was that branch and bound. What it is doing is it takes the estimated cost and refine the solution with least estimated cost, but unfortunately it also does not have any sense of direction. When we are only, as you know, from a star you have one formula, right? F of n is equal to g of n plus h of n. So this is in some sense guided only with the help of g of n only, not with h of n, guided using g of n. So whatever the cost we are finding till a particular node, it is taking only that. It is not taking how far the current solution is in reaching the goal. That we will be understanding when we do one problem. So, so that means it is not dependent on h of n. That's what I mean by no sense of direction because I have put here guided, and this statement can be contradictory. That's why I have put this guided using the path or the cost found till now, but not on the future cost. Okay, I took this problem from GA5. It has 5 cities and the costs are given. For convenience, all the costs are also given in ascending order. All of these numbers in ascending order they have given. I have put it in another way, like for each row, for A, there are 4 values. I have sorted them in ascending order also. So C56, B70, E84 and D130. Similarly, for B, I have sorted the values in this row in ascending order. Similarly, this is going to help me. You will actually see how it is helping. C, I have put D and E. So this is the initial setup. They have also given a graph. The first point is that a root node is considered, and always we are interested in finding what is the cost of root node. When I say root node, at the beginning, we don't have any knowledge of the graph and we blindly assume that A will be connected to, anyway, in the graph, when we want to complete a tour, each node should have two edges connected to it, right? So A should be something like this, so something, this is a valid tour. So each node should have two edges connected to it. So under blind, and the best estimation that we can do is each node will have minimum. We obviously our goal is finding the minimum cost. So for each node we will take the minimum values that it has. So I assume that here A is connected to C and B with these costs. B is also this cost. C is also connected. This is just a blind assumption, and we go forward to revise this assumption and reach a optimal path. So for S naught, how we will consider is we take these two nodes, and the cost will be for A, the two edge contributions are 56 and 70, and for B it is 58 and 70, and C it is 40 plus 56, and D it is 78, 80, E it is 40 plus 84. So the total is this. Here we see for A2, B2, there may be repetitions. See, AB I have considered, but again BA I have considered. In a tour, there are as many edges as the number of nodes. But here I have got 10 edges, so twice I have got. I need to reduce it by 2. So the cost of the uh, the tour formed with this assumption is 316. Am I clear till here, or am I going wrong or fast?
I'm clear.
Clear,
Clear,
ma'am.
right? Okay, so this is the, maybe I can open that GA5 as well. We can cross verify the answers. Yes. So lower bound, this we call it as lower bound because it cannot be more than, it cannot be less than this anyway. We are considering the minimum possible values and we have come up with a number. So no way that it is going to be less than this. So it is called a lower bound on the overall cost. That is why S naught is equal. Then we have this question of on what to revise. Here we see that we have chosen a particular edge, CE. What happens if I consider it permanently? One more thing that I need to cover here is under S naught, we don't have any permanently included nodes. We have only assumed that these edges will be there. Permanent inclusions nil. Permanent exclusions also nil because we don't know whether something can be completely excluded or we don't have any information as such. So we haven't decided what will be in and what will be out. So permanent inclusions are not there, permanent exclusions are not there. This is a bare minimum estimate. So the questions are not here. Maybe in some other PS these questions are here. And each edge, default means edges created under assumption or this minimum criteria, edges included using minimum criteria. we have included 10 edges using this minimum criteria. AC we have included, AB also we have included using this minimum criteria. BC, BA. So similarly for each node we have included 2 edges with this minimum criteria. So that is 10. That's what is happening with S0. Now comes the question of on which edge shall I branch this S0 forward? Here we see that CE they have considered and they are exploring what happens if I include CE permanently and if I exclude CE permanently. Why CE is chosen? That is because that is the least edge with least cost among all the edges as per this order they have given us to help, right? So CE is the first one always to be considered. We take the edge with least cost and then branch accordingly. So for this, what happens? So at S naught, our graph is just like this. No permanent edges. We have just assumed that everything will be connected to minimum. So when it comes to A1, we now know that permanently we need to include CE. So that is the consideration here. Yeah. So for A1, we need to permanently include CE and we need to check what happens and what will be the cost of it. When I say permanently including, it will be like this edge is always considered. Yes, this edge is always considered. It is not clashing with anything else, so I need not permanently exclude anything. Because CE is there, it doesn't stop me from taking anything else. I cannot, we will be more clear of exclusions when we have one more scenario of such. So now what happens of the cost? The cost is for A, earlier we were thinking that C should be there, B should be there. Now also we would go with the same assumption. For A, we will simply take 56 and 70 because A is free. We don't have any constraints on A at here. Similarly, for B, we don't have any constraints here. We will directly take the min values, 58 plus 70. For C, E, unexpectedly E is here. So this edge, we should definitely consider that 40. The next choice is what is minimum, is 56. For D, we don't have any commitments here, so we assume that it will have least costs. E, we have one commitment for C, so we should definitely take that C and we will take another one. 632 is the cost. Again, with the same logic that we have 10 edges considered, now it is also giving a 316 cost. This is the lower bound when CE is included. We see that the cost here and here is also same because this CE, but earlier also it was considered, now also it was considered. So to be more clear, if in case E is something like this, assume that E is something like C is here and what did I delete from here? 40. So in that case, how will we take the, just for a while, remove this, think that it is not there and this is something like this. Then how we will change our calculations according to this commitment. A doesn't have any commitment, so take minimum values. B also no commitment, take minimum values. C should be having some commitment here. Okay. C also I need to change. C E I made it to 98, right? So E goes here with 98 value. Yeah, so A is 56 plus 70, it will be there. B is 58 plus 70, it will be. C, now C is committed to E, even though E is at higher value, since I have made a permanent inclusion, I should take this 98 for C definitely. And the second edge, I am free to choose a minimum value. So these will be 98 and 56 will be the contributions for C. And D, No commitments, 78 plus 80. I will straight away take the minimum values. E again made one commitment with C. So 98 I will definitely choose. And the second contribution from E will be 40. This is how it would have been in case there was a different number for CU. Now you understood, right, how we need to change our values as we go along and include one by one edges into our graph. So am I clear till now? Hello.
Yes, ma'am.
Okay. Yeah. So this permanent inclusion, again, how many defaults we have? A has two, B has two, C, one edge is coming from the fixed permanent inclusion, one more alone is coming from the minimum criteria. So default contribution from C is only one, D is again two, E is again one. So the default counts here will be 8 only. Earlier default edges were 10, now default edges will change to 8 and the cost is 316 for this. Okay, I think I can go a little faster and do for A2. A2 is exclude CE. So that means we have this graph. Now we are not allowed to take CE even though CE is having a minimum value. Okay, let it. So now what will be the permanent inclusions? Nil. We didn't include anything permanently. Okay. So permanent inclusions are nil. Permanent exclusions, I have one because CE, it should not be there. Default we'll calculate. Now we'll calculate the cost. Okay. Is this still visible? Okay. A, I will go ahead and take the minimum values of 56 and 70. B, also there are no restrictions, so I will take the minimums of 58 and 70. C, now we have a problem. E is having a minimum value. I am supposed to take that, but my approach is saying that you should not take E under any circumstances. So I will go ahead and take the next best two. I will take 56 and 58. Okay, D is free of any restrictions, so I will take 78 and 80. E, again, even though C is at 40, I should not consider it. Consider the next best, 84 and 94. Again, divided by 2, you have the cost of 352. So that is the cost of A2. We are aiming at. We are getting cost is equal to 352. Is this permanent exclusion also clear?
Yes, it is clear.
Okay. So the cost of this is 352. Okay, now another scenario. Now we have next level. Been out of this 316, 352, which one will we proceed and explore next? We will obviously explore the one which is having a lower cost because we always want to reduce the cost of the complete tour. So our A1 is picked for exploring next because of this 316. I'll see if any of the questions are matching. Okay. Okay, so A1 is chosen for next exploration. So A1 means this graph we need to explore on this. Again, which here they have chosen AC and they are branching with the help of AC. How did they know when I explore CE, I need to take AC in the next level only? That we can understand with the help of this graph. I am exploring AC means I am continuing this graph. So I have already fixed one. I have already, oh, one minute, just give me a minute. Yeah, sorry. So this graph, I want to explore further and improvise it further. So there are, I have already an edge fixed. I want to extend this either this side, either here I want to extend and find a possible tour, or here I want to extend and find a possible tour, right? Extending means this I have considered. I want to explore here, hereafter, what will be the minimum. So for C and E, I have two rows here. This is C row and this is E row. Exploring means I find the next best value from there. Out of these two, I have already included CE is 40 here. So what is the next best after 40 in both of these rows combined? It is 56. E has 84. So CA is considered for next exploration. For this edge, whichever direction I want to further improvise is dependent on the values of these two, because C is in one edge of this one end of this edge, E is in another end. So I will take both those rows and explore which way to go next. So this value says me that you go to CA, that would be better decision. So I take this further graph, this graph further, like with the help of CA, and I branch it by including CA and by excluding CA. That will be my next.
Ma'am, I have a doubt, ma'am.
Yeah, yeah.
Here we selected AC after CE. If you scroll up, there is a in the question. It's ascending order was there, no, ma'am.
Ascending
In the
order
question,
is
distance was in ascending order.
this
Yeah,
one. Yeah, yeah.
yeah.
You can take from here also actually. I I made this for my convenience because I wanted to explore C row and E row separately, right?
Oh, okay, okay.
These two I want to compare and take the next best, not the next best from here. If the next
So
best is AD here, suppose.
after AC we should take BC.
No. See, after AC there was AB. After AC, what happens is, okay, I'll move forward. Just like EC, now I explored that AC is here. So this comparison told me that AC is the next best out of these two. As per your logic, you are saying after AC I'll explore BC. But BC is not in any ending of this already found path, right? I cannot
Yeah.
take BC hereafter. I should compare E row and A row and try to find which one is better than which one is the least cost. So in this case, when we go to the next level, C level branching, I should be comparing E row and the A row. I have already included EC40 here, and assuming that we have finished this level, AC also 56 we have already included. So what is the next best? Is 70. 40, 56 we have done, and 70 is the next best. Here 84 is there, no? So next best is 70. So next branching will happen based on AB. That is how from AC we are getting this AB branching. Am I clear in conveying?
Yes, ma'am. Yes, ma'am.
Okay, assuming that I am clear, I'll move ahead. Should I move ahead and do for everything or no? I'll change the calculations to include something more. Okay, so for B1, this is a graph that we are exploring. And we decided that AC is the next best out of E row and C row. So we are permanently including AC, right? This is a permanent inclusions are, okay. Permanent inclusions are EC, comma AC. Now we have, okay, now we have this topic of permanent exclusions. Now that this graph is like this, which edges should not come at all? AE should not come at all because it will make a loop, right? So including EC and including CA will permanently exclude my AE edge. Similarly, it will also exclude CB because CA has already satisfied two edge criterion meeting at a particular node has at max two edges. So C is already full, so it should not participate in any more edges. So CB I cannot choose, CD I cannot choose. So what else can I not choose? I think that's it. So now it is clear, right? How permanent inclusions and permanent exclusions are coming. Because it is like this, if I choose AE, it will get closed. So it is excluded. And CB is not allowed because C will have 3. CD is also not allowed because C will again have 3. So these are permanent exclusions. These ones we need when calculating the cost of B1. Cost of B1 will be at A, we are supposed to take C and B. Okay, C is matching with my commitment. So I will take 56 and 70 as usual. 56 and 70. At B, I was thinking that I will take C and A earlier, but now we see that BC is in the list of permanently excluded list. So I should not consider BC and move to next best alternatives, that is 70 and 78. 70 and 78 are the contributions from B. For C, C is committed to two edges, E and A. There is no more concept of minimum. Of course, it happened to be minimum because we are exploring around C only. So 40 and 56. For D, B and C, I plan to consider, but see that DC is coming as a permanently excluded one, so I should not take this C and move ahead. I can take this 78 from here, move ahead and take this 94 for D. E, C one commitment is there 40, and the next AE I plan to choose, but AE is also in the permanent excluded list. So I should not take AE, I should take B, 94. 676 by 2 as usual, we'll get 338 as the cost of B. That's how we are exploring and forming all this. If we move forward and increase the number of edges, so let me take this case. Okay, excluding AC, that's okay. Let me quickly jump to C1 and show you how some edges are forcibly inserted. Now we saw only the case of forcible exclusions. This edge excluded, so these three exclusions are forced. So let me also show you forcible inclusions. Okay. So for C1, CE is included, AC is included, AB is also included. That was the next step. AB is also included. So what are the forcible exclusions, forcible inclusions it will do? B needs one more edge. Can that be E? B already has one commitment. It needs just one more edge to fulfill the criteria of that tour. Can that be E?
It should form
No.
loop.
It will form loop, so it will not be. Can that be C? No, because C already has two. So B, C is not okay. I'll draw
The
the next
BC
one.
is already permanent exclusion
Yeah,
in
yeah.
B1 you are doing.
It will form a loop. So E is not allowed. C we should not anyway because C will have three. So the
Madam, CB is already
permanent
in B1 you have
C,
excluded. The
yeah.
permanent
So it
exclusion in CB.
yeah, yeah, permanent exclusion is there, but C already satisfied its two criteria, its two edge criteria. C has already satisfied. So B cannot go to C, and we saw that E also it cannot go. So it forces me to choose BD. This is forced, right? And since this is forced, now I have only one option. D wants one more. D cannot go to A because A is already full. D cannot go to C. C is already full. D already went. So this is also forced. First, this one is forced, and next, this one is forced. Because of the three inclusions, other two are forced. So now my graph is full. I have five edges, one, two, three in blue, two in green. So my graph is full. That's why C1 has become the leaf node. Once the graph is full, either with exclusions or inclusions, we find out that this is going to be like that. It is going to be an edge tour. And out of all such things, we will find the best tour. I can show you one more case, or this case also. C1 is forming a tour like this. We can see. Okay, we can see with C2 also that it will force some edges and it will close the tour. Let me show for C2. Yeah. So for C2, CE should be included, AC should be included. Okay, we have done that. And AB, they are saying they want to exclude. AB, they are saying it should be excluded. Now it forces some more edges. So now A wants 2 in any circumstance, but it cannot go to B. C is already full. It cannot go to E because it will form a loop. So A is forced to go to D, right? One more thing, another thing is D also needs two edges. It cannot go to C because C is full. It cannot go to E because that will form a loop here. So D is forced to go to B. And here we see that this is again forced to complete the tour because there is no other option to go. So two inclusions and one exclusion forced me to make three more inclusions. This is also forming a complete tour. That's why C2 is standing at the leaf node and there are no further ways of refining it. That's what happens with others also, other edges also if you work on that. Am I clear till here?
Yeah, one observation is once you decide on three edges, for example, for a five nodes, five CT2, if three edges are decided, whether you include or not include, then
Yeah.
it is you will get a valid tour with two more edges you will add.
Maybe.
Correct, madam? What
Yes.
I'm trying to tell.
Yeah,
Once you
yeah.
decided, for
Two
example, in
inclusions and one exclusion is also sometimes forcing.
yeah, yeah, decided. That's what I told. Decided.
This side, yes,
Whether
yeah.
you exclude or
Maybe.
include, but you have decided on three edges. Maybe two inclusion, one exclusion,
But
or two
no,
exclusion, one inclusion.
no, no. That in that case, C3 should also have been stopped, but it continued to D1 way.
So minimum is for two inclusion should be there.
If two inclusions and one exclusion, see here also two inclusions, one exclusion, but it completed. This also two inclusions and one exclusion, but it went on extending
Okay. I mean,
at this
here
part.
in C1, one exclusion is there and two inclusions are there, but still it is going. Okay, okay.
Ah, no, no, but it's still closed. C2 is still
C3,
closed.
C3,
Yeah, yeah. C3,
C3.
there are similarly two inclusions and one exclusion, but it went on.
So it is not a
Right.
general formula you can decide.
Maybe, yes.
Okay.
So that's why how they are doing. Let's go to the questions and see. Number of tours represented by B2. We'll do that. This is
And one
B2.
observation, one okay, you finish, ma'am. Sorry, I will come
Yeah,
to
yeah.
the end.
Number of tours represented by B2 is the question. So B2 is nothing but include CE, exclude AC. Okay, I'll take this from here. Include CE, copy, and then for B2, include CE and exclude AC. Okay. This, how I generally do is, for a tour, there should be all 5 nodes sitting in some arrangement, either A, B, C, D, E, or whatever fashion. Some arrangement will be there. CE is included. CE segment, it is included. What is answer? Okay, good. Okay, CE they are saying included. So this edge is fixed for sure. And CA should not be coming. So they are saying this should not be A. I'm just putting it in another dimension. That's it. Just on a circular fashion. Anyway, tour is a closed path. So CE they want me to include and CA. So this point it should not be A. That's what they are saying. So it should be either B or D. Only option here because C is other end. One. Okay. Yeah. So C's other end of connection should be either B or D. Okay. If at all, I take for this scenario. So B is here. So B will be coming here. So what are the other options? A and D should be arranged in these two places in 2 factorial ways. Right. A and AD and DA. Similarly for D, D will be fixed here and A, B will be allowed to arrange here. So that will be again 2 factorial ways. So total we will get 4 ways. That's how I do. I find this easy than looking at this graph and making some stats. Is this logical or bad? Whatever.
Yes, actually. Observation in PYQs are we are getting A, B, C, D, E, F.
Even for that also.
I'm just telling there are 6
Okay.
internal questions is okay, but we just to learn we are doing for 5 cities, but it will be
Hmm.
6 cities.
Yeah,
Uh,
yeah.
Normally they are giving.
Yeah, so this approach is helping me in doing like this. Maybe I can show you for number of tours represented for C4. Let me do the same first. C4. What is C4? CE exclude AC and BC both. CE is there, exclude AC and BC both. Okay, I'll draw same circle. CE they said should be there. Exclude them. So there are 3 more points. Exclude AC and BC. So here A also should not come because AC is excluded. B also should not come because BC is excluded. So only option for this point is D. D is fixed here. So there are only two choices left here, A and B, and they can be arranged in 2 factorial ways. That is 4. Sorry, sorry.
4, 2 only,
No,
no?
2, 2, 2, 2. I was looking at the 4 above and I wrote.
Ma'am, I think this is the easier way.
Okay. So this is 2. Yeah, this is helping a lot actually.
Mhm. Have you seen any exception where this is failing?
Not till now. When they don't give any inclusion or exclusion and they just will ask what is the number of tours, we need to be careful because this is cyclic. We
Mm-hmm.
cannot just say 5 factorial because
Yes, yes, yes.
ABCDE and EDCBA will also be same, right?
So it will
Because
be
since this is
it will
it
be
will
five.
be
No, no, ma'am. It
no
will be
4
five.
factorial by 2 or
Ah,
something like
4
that.
factorial by
n minus 1
Yeah,
by n
ah,
minus
n
1
minus 1
factorial by 2.
factorial by 2. Yeah,
2.
yeah, n
Yes,
minus 1 factorial by 2 it is.
right.
4 factorial by 2 it will be. So that cyclic thing, we need to be careful when we are doing like this on a approach where some are fixed for sure. I am following this. Okay, I think enough of T and TSP for branch and bound. We see first 4 nodes refined by BNB. So first one is always S naught. Then we explored these two, 316 we found. So A1, the exploring is based on cost. So A1 should be the next one. And once I explored B1, B2 we get. So then we compare B1, B2 and this 352. So out of these three, we will decide which one to go further. Maybe it might have, yeah, this is, yeah, cost of 331. B1 I have 338. A2 is anyway at 352. So somewhere B1, B2 should be coming in. So the answer is okay. B2 might have given a lesser value. So B2 and B1 are clear even before going to A2. So if we explore the costs, it will give the thing, cost of optimal tours. I think that's it. Any other question that we want to solve? Oh my God, 44 minutes over for BNB.
Madam, how practically pen and paper when we are doing, I mean, that how it was there. Um, how we are going to do actually?
Ma'am, can you
Yeah,
solve this question that I shared initially? Uh,
that permanent some cost or
yeah, yeah,
something.
yeah, yeah. That one.
Can you give the screenshot? Actually, we have many more
Okay,
algorithms.
okay. I'll send it to you. I'll try, and
Okay,
if
Yeah,
this
I'm
will be
able,
we'll,
I'll send it to you.
yeah,
okay.
yeah. With
This,
this input, you try, and if
I
you're
think
still
I'll
stuck,
be able to. Okay, okay.
we'll
Thank you.
do that one to one
yeah.
because
What
we're
is that?
still here.
Sorry. What is that you are planning now? All what are the algorithms?
Yeah, whatever algorithms are there, we are doing at least one problem from each algorithm.
Okay, how many you have finished now?
One.
Okay, this is the first one. Oh, okay.
Ma'am, ma'am,
BNB.
ma'am, the important question: how many algorithms are there?
BNB.
A star
A star. That's min max, alpha beta pruning, and triple star. That's it.
in A star
GST
itself
is
we have A star with W2. I mean, wait.
no, no, that I'm not doing W and yes, both are same, no, just
You have to multiply.
multiplication.
Yeah, yeah, yeah.
Yeah,
No,
A
no,
star
I'm not
and
doing
one
Ma-
more they have asked is B and B repeat close note. Okay, this one.
okay, so this is for a different graph, BNB. I'll take it faster from here. This is for traveling salesperson, this kind of information, and believe me, this kind of ordering is helping a lot. So this is pretty much encouraged. So
In
the
the
next,
question paper they are giving the ordering, ma'am.
no, 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 this is different. That is different. This they are
Not
giving
this,
for all the
not this,
nodes.
not this. Whatever you have written, no.
Yeah, yeah. In PYQs, few PYQs they gave this. Yes, yes.
Only few. Okay, I have not seen. Really. Hmm.
Okay.
Okay.
Maybe in some they didn't give, but okay. This is helping. If they give that, we are lucky. Okay. Next one is BNB one. So this is this kind of graph. This is simple. Let me take my book. I have already put this graph, so it will be easy for me to draw again. Yes. Okay. So as always, we'll start with the first node, S. It has two connections, A and D. For B and B one, what is happening is, okay, I'll tell that when it comes. A and D. For A, what is the cost from S? It is 4. Better we write it next to this. And for D, what is the cost? It is 2. Then we explore A. A has 4 edges, S, D, E, and B. So this is the point where I
Madam,
wrote
we
the 2
can
plus 1.
explore anything, or we have to explore the shortest one.
No, no, that will come when you write the number again next to it automatically, right? Just I'm writing all the children of A, that's it.
Okay.
Okay, sorry. Right, we need to do D. D first because D is 2. This is what you are saying, right?
Yes, madam. Yes, madam.
Yes,
You
yes.
should
We need
take
to
the
do D.
shortest one.
Yeah, we
Low.
take the short out of this, take the lowest one, 2. D has 3 children, A, A, E, and S. S is because BNB1 makes us to repeat the closed nodes. Even though S is already closed at the top, we will write again. So for A, the distance from D is 8, but D already has 2 here. For this 2, add this 8, so this will become 10. D is already having a 2 distance here. For E, we have 4 more, so this will become 6. 2 plus 4. Similarly for S, D is already having 2. For going to S, it is 2. So this is 4. 2 plus 2. It is like SDS. The length of
Yeah.
SDS is 4. Right? We can see that from graph also. I just go
Is it that we have to calculate how is the heuristic plus the assigned
No,
value?
no, not heuristic, not heuristic. BNB is not dependent on heuristic. It is dependent on the actual costs only, the G of what I wrote, in the beginning. BNB is not taking consideration of heuristic, not dependent
Because
on HM.
BNB is not direction oriented. It's not going towards the goal.
Yeah, it's guided, but not towards the goal. Guided only with the actual cost that it has in hand. So
Yeah.
only with the graph values. Okay, so similarly we extend. For out of these, we will see which is the lowest now. 4, 10, 6, and 4. Right, 4, 4 are same, but we generally take with the help of alphabetical order. So we write for A. A has 4 children. 4 children are S, D, B, E. S, D, B, and E. A is already having a distance of 4, and towards S it has again 4, so it will become 8. So it is like SAS. What is the distance? SAS will be 8, right? So similarly, D. A has 4, and towards D it costs another 8, so it will be 12. You can see from the graph also SAD, that is this 12 means. So SAD will give me 4 plus 8. Similarly, D. 4 is here, add this 3, so 7. So like this. Similarly for E, 4 is here and this 12, 8 gets added. So it will become E12. Like this, we need to continue writing. So next one to explore will be S4. It again has two edges, A and D. Write the values. Somewhere we'll hit G. That is about B and B1. It has nothing much than this. So I'll quickly move forward towards BNB2. What BNB2 does is it will not repeat closed nodes, right? So just like we do this S, we will write A and D. When we are exploring D again, I will write only E and A, not S this time. That is the difference. Do not repeat closed nodes. That is what BNB2 is. Similarly, the calculation is same. The S A first time when you write it is 4, D is at 2. Next, if you want to go to E, 2 is with D, and I need 4 extra of distance, so it is 6. So SDE is 6. That's what I mean. This 6 means how much it is, what is the cost of this part. So somewhere in writing you will go somewhere and you get G, no? So by the time you already have a number next to it, that is the cost of the path. Otherwise, you can just cross verify taking it something like this and calculating from the graph also. This I find the easiest way to write the number next to it. It gives me quick access to what 2 is here. Okay, for E, I just check this edge and add that. Take this 2 here and add this 4 here. Easy access. I'm facing. So that's one.
Additionally, if a little
Yes.
another 5 seconds are there, additionally you can do between S and D you can write 2, next to D you can write 2, and
Yeah, yeah.
between E and D you can write 4, next to E you can write 6.
Yeah, yeah. That will be too many numbers in our graph. Okay, whatever is comfortable, that's okay. So we'll move forward. Any questions from anyone? Let's see.
One of the questions is asks whether the heuristic given is correct or wrong, or it is something like that. But what
Admissible, huh?
pardon me?
Admissible.
Admissible? Yeah, maybe you can say admissible to get
Okay, after A
validation.
star. After A star, we'll come to admissibility.
Okay, okay. After A star, you can ask that question. Okay.
Hmm. Okay. So BNB, we saw that it is only taking care of G of n, but it is not being influenced by the goal and the estimated cost towards the goal or whatever. That H of n is not influencing D of n. So we are considering that also, and we are seeing it A star. So f of n is G of n plus H of n. This is the cost that we are mainly concerned of, and we take all the decisions based on this. We know that B of BNB works only on G of n, and best first, it always only blindly sees H of n. So in other words, we can say that A star is a combination of these two techniques. It will combine. G of n is the actual cost that we see from these edges directly. H of n is the heuristic estimated cost based on heuristic function. If they give Manhattan, we take Manhattan, or otherwise they give Euclidean. Okay, Euclidean, whatever the function that gives. As always, we will explore the nodes with least value of f of n first. Right? I have written heuristics here also. Yeah, heuristics. For A, the Manhattan distance is 4 from G. For B, it is 1, 2, 3, 4, 5. So similarly, I have calculated the heuristics and I have written here. Do you want me to make a graph and complete this, or shall we move ahead? So the initial one will be S. It has two nodes to explore. One is E and another is D. For E, the actual cost is 8 plus the heuristic
26.
cost is 18. So it is 26. This is
D,
painful
D
here.
will be
I'll
30,
do,
D will be 31.
I'll do that in Excel. Okay. So S, it will go to E and D. For E, the value is, yeah, E, the value is 8 plus 18, which is equal to 20. And for D, the value is what?
31.
It is not giving me an answer right now.
You just
20 plus 11.
No, what it gave me, it is alt plus. Yeah. For D, the value is 20 plus 11, which is 31. Okay, so now out of these two, we will explore the least one. So this one.
11,
So
11,
E,
no?
no,
Oh,
it is
31,
31, right?
31. Okay, sorry, sorry.
mm,
Go ahead, madam. Sorry.
It is 31, right? So the E is the second one that we explore. E has three, but S is already closed. So we have only two options, F and D, this way. So
Ah,
F is it? Yeah, similarly, just like how we did in branch and bound, E already has this distance of 8. To this 8, add this EF distance, that is 12. It becomes 20 totally, and the heuristic of F is 10, so that is 30.
30.
And B, We
16,
will put, no,
16
we'll
plus
put,
11,
I am
26.
trying to mark the nodes that are already done. This is already done. So D is not yet done, so that's why we are exploring. Otherwise, we would not have explored D once if it is done. D, E already has
Is
8. Yeah, and to reach D, it needs 8 more. So it is 16 plus
11, 27.
11. So that is 27. So since we have an improvement for D here, we will ignore this D. We will not explore this any further. We will leave this. Yeah, we will ignore this D and we will consider only these two. Again, from this, what is the least cost is D. So this we will do next. That's how we proceed in A star. Wherever we get a better value, ignore the earlier open condition of that D and explore from here. D, we have again 4 nodes E, F, B, S, but E is already closed, so we will only, S is also closed, so we will see only F and B from D. F, if we find a better value than this 30, we ignore this 30 and extend this F. So, shall I do that or we'll move ahead? Anyone?
I'm okay with it.
Okay, I think we can move ahead. Okay, so that's how A star is, and W is, and we have this admissibility. So admissibility is we put that this B and A star are capable of finding an optimal path under certain conditions. So that certain condition is this conditions for admissibility. It is nothing but a simple equation that h of n less than or equal to h star of n. I'll explain what this is. H of n, we always know that it is the heuristic value, whatever Manhattan or Euclidean, what they give. H star of n is the actual value, actual values that we see on this graph. So for each node, its heuristic value should be less than or equal to its actual value in reaching the goal. Why do we need this? Because when estimated is less than or equal to actual, the algorithm never goes overconfident because it knows that actual is always greater than this, and it calculates or it picks the paths cautiously. It won't miss the optimal path. That is how I understood it. Because the actual is always higher than this, and my estimates are always going to be lesser. So it picks the optimal path without missing. Okay, let me show you this graph. Here, for each node, if you see, for node, okay, I'll start with C because that's where this is failing. The estimated is the heuristic h of n, which is equal to Manhattan distance is 3 from C to G. But actual means min cost from C to G in the graph
It's 2.
is 2.
It's
So
failing.
estimated less than or equal to actual is failing. So this graph is not admissible. For every node you need to check for all nodes because C is here and it is very evident from this single calculation. There are other nodes also which fail this. For D, in case you see. For D also, if you see, the estimated h of n is Manhattan, which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But actual min cost to G is 4 plus 4 plus 2, it is 10 only. D, E, C, G, it can go this path. It has very minimum cost. Actually, it's 10. But we need to be careful in taking this minimum cost because you may see D, A, B, C, D, A, B, G path and think that it is 11 and 8, 19. So H of n is less than or equal to 19. That passes. No. we need to carefully take the minimum cost from D to G.
So
Use
any case,
Dijkstra. Yeah,
so
yeah.
if any case it fails, so that means it's failing entirely.
Yeah,
Okay.
yeah. Any one node it fails, the whole that heuristic function for this graph is not admissible. So not admissible.
In other words, with that heuristic function, you cannot find the minimum
You cannot
distance,
find an optimal path to G.
optimal
If
distance
you
or
change the
optimal path.
heuristic function to Euclidean or whatever, maybe it can give a different values because h of n will change, right? When we change the heuristic from Manhattan to Euclidean, that case may be different. I have one more option which gives admissible. Yeah, this graph I took from Google. C to G for C, if I write the heuristic values, they have some function and they gave their values directly. H of n they gave as 1 and minimum cost is 3 actual cost. So it satisfies. Similarly for everything, if I take the last B node, the H of n they gave as 1 again. Min cost is, there is only one way, I think it is BCG. So it is 2 plus 3, 5. So it is again passing. So similarly for all the nodes. S also, H of n is 2. Obviously it is every edge if you add, no, it will definitely, min cost will definitely be more. It is 3 plus 3, 6 here, and SESEG it is 5 only. The min cost is 5. So passes. So this graph is admissible. That's how we need to do. But the only point for us to be careful is finding the minimum cost. I think we can do that easily with the help of Dijkstra algorithm or whatever is feasible.
Yeah, BNB.
Yeah. No need of GNB. Dijkstra is easy. We start at G and find the minimum cost to all. No, take
No,
from
instead
this.
of that, BNB will give, BNB is sure to give minimum cost, no? So if you are finding BNB will give
This
minimum
BNB,
cost,
right. We can do this also. Yeah, this also. You can do. Yeah,
yeah.
whatever algorithm, take the minimum graph and minimum
Because in
maximum.
the quiz 2, they are asking all like A star, W2, and then BNB. And
Okay.
then they're saying whether the heuristic given is admissible or not. So one
Okay.
faster way to at least one small checking is if BNB is giving a lesser cost than the A star, then obviously the heuristic is not admissible.
Sure. Yeah, yeah. Because BNB is
Observation.
only taking the actual cost. Yes, yes, I
Yes.
understand. Okay. So I think from week 5 we have only these two in plan. If you have any more doubts, we'll do that one to one. Okay, in week 6, first algorithm we have is WA star. It has no big difference from A star. Only thing is wherever you find H of n, you multiply it with W, and rest all process is same. Why we needed WA star is in A star. If you remember, we are just giving this equation of G of n plus H of n. We are taking the actual cost and the heuristic cost with the same weightage. We are not giving more weightage towards heuristic or more biased, something like that. So giving more weight to heuristic actually shows less need to search and finding the path easier. That's what I read. So we are giving a little more weight to heuristic by multiplying with W. So f of n will be g of n plus W into h of n. Yeah, when we say weight, we cannot just keep on increasing W because in that case we miss this role of G of n, and again we fall in finding the optimal path. If we go to 0 also, we are not confident in finding the optimal path. If we go very high, this gets ignored, so that also will not give you optimal path. So that's how the importance of W is. WA star is just like
Madam,
A
just
star.
an observation. If W
Yes,
is
sir.
0, it becomes branch of
BNB.
BNB.
Yes, yes, because BNB is only taking G of n. And if W is very high, it becomes this thing, best first, because only H of n is considered and G of n is ignored. Right? Best first, that was what we are doing. No, we are only
Correct.
taking the heuristic values and going directly. Yes, that was there in the lecture also. Sir was mentioning that. If
Yeah.
W is high, it acts like best first. Okay. Okay, we'll quickly move forward. The next algorithm is SMGS. It has this concept of boundaries and kernels. It is purely done for memory management because this A stars and all, they are keeping track of all the open nodes, all the closed nodes, and also whenever memory is full, there is this concept of moving from boundary to kernel and removing that. I just went to the 3D, and if I am not wrong, yesterday in live session, Bhaskaran sir was saying that we don't expect SMGA in quiz 2. So with that point, I haven't taken any example of doing it here. Similarly, with beam search, I just read theory, top K nodes will be maintained and delete unwanted nodes immediately as and when they appear. So this is also not optimal. I am not touching this, doesn't mean it won't come in quiz 2. I am again telling I don't have any confidence on that. But just for time's sake, I have not touched.
Ma'am, Bhaskaran sir has said na ki it is not important.
He said like they are heavy to do by hand and we don't expect such questions in quiz 2, but I may have heard it wrong or he might have something might have happened, but after quiz 2 question paper I am not responsible.
Yeah, yeah, yeah. Fine.
Yeah, so he just said that these are heavy to do by hand. So that's right. And in PYQs also, I didn't find them many. So I haven't taken them. That's it. Nothing related to quiz 2. Okay, so week 7, many important algorithms. Okay, the first of all is strategy. Strategy means being ready for. There are two players in this game theory. One is max and the other is min. By default, max is shown with the rectangle and min is shown with a circle. So strategy means whatever min chooses, whatever the opponent player chooses, I have a plan in my mind to go in which direction. So strategy of max will be at every judging position or at every choice position, I am ready with one choice in my hand and I am ready to face all choices of min. So for this graph, if I want to write a strategy for max, it will be like this is one choice position and I think I have an answer in this choice. And I should be ready for whatever min chooses. And again in this position, I prefer to go by this way. Here also in this position, I prefer to go by this way. And I should consider all choices of min. This is the default. This is one strategy for max. Right? So in this case, we see we see that whatever leaf nodes that are coming in this strategy, they are horizon nodes. In this strategy are A, B, E, and F. These are called horizon nodes. There can be different strategies also. Suppose Max need not take this choice always. He can say that, okay, I'll take this choice here and I'll be ready for Min's blows towards me. And at this juncture, I want to take this choice, not that way. And in this question, I want to take this path, and I should be ready for Min's answers, and I should be ready for Min's answers. So this is also in another strategy. This is for green strategy, and horizon nodes in red strategy are again C, D, E, F. So to any node can be a part of many strategies. Horizon nodes are not restricted to a single strategy. So this is how we find strategy. So yeah, strategy I wrote, take one choice at max, all choices at min. This is the mantra for finding the strategy. Okay, now the next question is best strategy. How do we find best strategy?
In quiz, will they mention the strategy, or it's a by default strategy that we have to follow?
By default, actually. By default, we are taking the left decisions. Whenever decision point is coming, we go going by left. Left. Strategy one is always taken on left decision. This right strategy and all will not come. But when it comes to best strategy, it is specific. Obviously, one best will be there. No, random strategies means any number can be there. Of course, there is some formula to find that number and all. It is there in his course. Okay. So now we find best strategy. So best strategy is the one which gives the max outcome, right? Because max player is always interested towards finding the maximum outcome. One way of finding best strategy can be explore all such strategies. For each strategy, find out what max is getting and which strategy is yielding the better value. That is the best strategy. So that is one thing. But another way, I don't know, everybody does like this, or I am doing like this. But another way I found is, first of all, fill this graph from bottom to top using this min max approach. This is a min node. 11 and 70 is here, so this should be getting 11. Similarly, this should be getting a 48. This should be getting 53. This is 74. This is 23. I don't have writing pad. Please bear with me. This is 30. This is 15. This is 45. Okay. We are filling from bottom to top. This is a max node. He likes 48. Here he wants 74. And here he wants 30. And here he wants 50. Again, this is a min node, so it needs out of these two 48, it needs here he needs 30. He'll take 30. So the max is 48. Okay, once we are done, these are the values. Now strategy. Strategy means max player should take the decision, right? At
Follow
this particular
48.
Yeah, at this particular point, Max has these two choices in his hand, 48 and 30. Which side will he go? He'll go to 48. So this will definitely be his strategy. And then, as we said, we need to be ready with all choices taken by Min. So this two. And again, at this particular node, Max has these two choices, 11 and 48. Where will he go? He'll go and pick 48 only. At this node, he has 74 and 53. Max will go 74 because that is his best plan always. And he needs to be ready with all choices of min, C, D, G, H. So this is the best strategy. Whatever is shown in red is the best strategy. Red is equal to best strategy. Its horizon nodes are C, D, G, H. C, D, G, H. I think I took this question from one of the okay. PS or GS, I don't remember, but that is correct. 1170 is that one we are doing? Yes. Okay, what is the min-max value of the game? Whatever value comes at root node, that is the min-max value of the game when we fill from bottom to top. That is, list the horizon nodes in the best strategy. Yes, C, D, G, H are the horizon nodes in the best strategy. This is the answer. We can check. Yes.
Ma'am, can you
Okay.
please repeat what are horizon nodes?
Horizon nodes in after filling all this red, whatever leaf nodes are coming for this red one, they are horizon nodes. C, D, G, H.
Okay, so what was the question?
What are
Okay,
the horizon nodes in best strategy?
okay, okay, fine.
This is the best strategy that we found. After filling all the values, take max decision based on these numbers. Otherwise, every time we would have blindly went to the left side. No, at this
Hmm.
this is okay. But here we would have gone by default value. We tend to go left, but that's not best strategy. This is best strategy based on these numbers. So go right here and
Then
take
can you
this.
repeat this how you are getting this? I'm a bit confused. I guess I'm some problem.
No, no. From the leaf nodes, I filled the
Yes, ma'am.
tree to the top.
Right, right, right.
After that, at each what is needed for a strategy. Max should be able to choose a best plan out of the two
Right.
available paths, right? So
Right.
at the first root node, he has 48 in this side, 30 in
Mhm.
this side. Where
Mhm.
will he go? He'll go towards
48.
48 only, because he is a max guy.
Huh.
And for strategy, we will take all children of min. That's what we were saying, right? So all
Yes.
children of min will be there. And again, at this point, 48 is here. He is a max node. He has 11 and 48 in his hand. He will go to right,
Uh-huh.
because 48 is the max value. And then we need to be ready with all whatever choice is taken by the opponent player. So
Uh-huh.
these two paths. At min, take two values. At max, take the best option. That is the best strategy.
EDGH will be the answer.
CDGH will be the answer. Yes, CDGH is the horizon nodes in the best strategy.
Okay, ma'am.
See,
Next
in
is
that previous question,
Admissibility.
one additional question I can ask is, Madam, can you show me this? 48
Yes, yes.
answer in the PA.
Yeah.
Question is, what is the min max value they are given now?
Hmm.
Similarly, I can ask if min is not playing optimally, what is
Hmm.
the value max can get?
But
Max
ma'am,
can
they,
at max get 48 in out of this game only, no?
No, madam. He can get if min is not playing what you call optimally. For example, instead of 74 in the level 2, no min can select instead of 50 74, he can play even 94. Min is not strong player.
but sir,
Okay.
it is always assumed that they will play perfectly.
Now, that is why I'm telling. I can ask as a
Yeah,
question setter. I can say they are not playing perfectly.
yeah, yeah.
You understood my point?
Yes, yes. So you will say 74. No, he'll. But
No,
whatever
in
Min
case
does, I am no, no. In a strategy, whatever Min does, I am ready to accept both sides of Min. No,
yes,
this side
madam.
also, I'm taking.
Yes, but in the instead of 53 and 74, Min could have chosen 88 also or 94 also. No,
Okay, that one itself you are saying.
yeah. See, Min is
Ah,
a child. He doesn't play optimally.
okay.
So in that
Okay,
if that
whatever.
type of question comes, I just thought I should share what I felt. So I'm just sharing.
Okay, we'll explore that. Okay, we'll move ahead.
Okay.
So, I don't know whether I'm clear in conveying this. Shall I proceed? Okay.
Yes,
Yes,
please.
I
ma'am. Ma'am.
expect this as an S. Okay, alpha beta pruning. Yeah, I found a simple way of doing it from one of the YouTube videos. I'm sharing the same. I don't know the logics behind it. Whatever. So what we do is start from the bottommost layer. Whenever the condition is max is given by is assumed to be an alpha player, min is assumed to be a beta player, and alpha less than or equal to beta is needed always. Whenever there is not, we need to prove. These are the, yeah, alpha less than or equal to beta is always needed. So we from this graph we can understand that whenever there is a box, it is an alpha. Max is an alpha means alpha is represented by, and min is a beta means he is a circle. Okay, whatever. Leave. Leave that. Okay. Now what I will do from the bottom, I try to fill the values and keep an eye on this condition. Wherever it is failing, I'll prune accordingly. So first of all, this min guy, first we will go to the downmost, leftmost direction. And for this guy, there is no value. We take from here 10, and whenever we want to go in the another branch, we will see if any of the condition is failing anywhere in its parents. If no, only then we will proceed to explore the next branch, another branch. So conditions, there are no values anywhere, there is no failing. So I will happily move ahead and explore this also. This is 11. So this is not going to get updated. This value is always a 10 from here and here. So next, move a little upwards. Give this 10 to its parent. Now these parents need to explore the right side. To go to right side, check if there are any violations above. There are no violations still here. So go ahead and happily explore this. Okay, for exploring, I need to come here. So this is 9. This will get 9 from this person, sorry, this node. Now I need to go right. For going to a different branch, for branching, I need to check for violations. There is a violation. Alpha is a rectangle and beta is a circle. Alpha less than or equal to beta is violating here. Alpha is 10, beta is 9. Alpha less than or equal to beta is violating. So I will not go any further. I give up. Whenever there is a violation, they give up. Okay, so that's it. I gave up,
So
came
this is
here.
called alpha pruning or beta pruning.
This is called alpha pruning. Whenever
Yeah.
a cut happens like this and there is an alpha node below it, this is an alpha pruning. Whenever a
Once,
cut happens like this, there is a beta node below it. It is a cut. Okay, cut.
so ma'am, one
Below.
question. So if
Yeah.
alpha is greater than beta, what have to do? And if beta is greater than alpha, then what have to do? So I'm just confused.
No,
Is there?
we are free to explore only if alpha less than or equal to beta. Whenever this condition is violating, we
Mhm.
prune and we don't go any forward. That is
Okay.
because, see, beta has, there is a theory, what is that? That theoretical concept is beta is having a 9 here. Beta, since this is a min guy, this value, even if it is 12 here, it won't accept, right? Beta, this fellow will always be less than or equal to 9. One side I have seen 9, so my value will always be less than or equal to 9, right? Because if 7 is here, 7 would have come here. If 6 is here, 6 would have come here. If 12 is here, this will be 9. This will stay 9 only, right?
Yes.
And
Yes. Yes. Yes.
is
Yes.
it clear? I went one side and found a value. Next value, if I see, if that is a lesser value, I'll get updated. If that is a greater value, I'm going to ignore. So for beta, there is no more scope of getting any value more than 9, right? After this, once I finished and came back with a 9 here, I am sure that this node will be less than or equal to 9 always. Right, till here, is it clear till here?
Yes. Yes. Also, I can see in a different like so
No,
10
I'm
is
not
max.
finished yet. Wait. No, I'm not finished yet. So this value, even if I see the right side or not, I can say that this is going to be always less than or equal to 9. But what happens at this 10? I have a 10 from here, and you are saying that you are going to be always less than or equal to 9. Why do I encourage you to go and explore further? Because you're going to be greater than 9, and I am an alpha guy. I need bigger values. So, how much ever you get in this node, I'm going to proceed with 10 only, right? You get the point? Beta, if
Yes.
it goes down also, it can fetch values below 9 only. Why do I need to allow it to go and bring something less than 9? Because I'm anyway going to reject it and take this 10 because 10 is coming from me from this side. That is why we are pruning here and we are not allowing the algorithm to take this step ahead because that is not going to favor us. That is the concept behind. But this less than greater than tracking at every point is becoming tough. So that's why we are checking. We are just saying above and seeing if there is any violation. That's what we are doing. But if you think theoretically, this is the reason. If you go and check also, this will always be less than or equal to 9. Why to go? And if you are less than or equal to 9, I have a 10 here. Why do I need this anyway? That is the logic. Yeah, you were saying something or shall I?
Yes, yes,
You
please
can go
continue.
ahead.
Yeah. So okay, 10 is here.
10.
I'll give this 10 here. And to explore, I need to check any violations. There are no violations currently. So I'll go down, explore from here. This is a 14.
14.
Yeah, 14 comes from here. And there are no violations as of now. So I happily go and explore the other also 15. Then it will bring 14 only. So this 14 goes back, we get here, we have a violation again. This beta is sitting at 10, this circle is sitting at 10, alpha, this is 14. Alpha less than or equal to beta is violated. So I won't allow you to go to 10 because the same logic. This is an alpha, 14 already is here. If you go also, you will go and bring something more than 14 you will bring. But I don't want you to bring more than 14 because I have already 10 here. So don't go any further, prune here. That is the logic. But I'm simply saying in easier ways that 10 is here, there is a violation, prune, don't go. So this is prune. This is a beta cut actually. See this figure. Cut and below cut there is a beta node. So this is a beta cut. Here below the cut there is an alpha cut. So this is an alpha node. Okay, we'll go back. 10 is here. This 14 is ignored because this beta will like this 10 only. Take this 10 here. 10 will be here. And next, I need to go. There is no point of violations above. So I'll go here, go down, explore it from the leftmost. I'll go 5.
2 no, ma'am.
No, no. First we will explore left always.
Okay, okay, like that. Okay, sorry,
Like
correct.
that. Now there is a violation. This is alpha 10. Beta is 5. There is a violation. No. So I don't go.
So, so ma'am, do we check the violation of the immediate parent or the
No.
super
All the
parent?
parents above. All the parents above will check. This is a beta. Here there is an alpha. There is a violation. We don't go. Give away. Just give up. 5 to go right side. I don't have any violations. This is an alpha, this is an alpha, there are no conflicts. So happily go, take this value from 4. This value is 4. Again, there is a violation, alpha less than equal to. So this is also proved. Give up. So this is an alpha guy. So 5 is coming from here, 4 is coming from here. He'll get 5 only. Take this value to here. Do I need to go right? No. Because this is alpha, this is beta, there is a violation, alpha less than or equal to beta is not satisfied, so I don't go. This is an alpha cut. There is a cut here and below that there is an alpha node, so this is an alpha cut. This is a beta cut. Sorry, this is also an alpha cut. This alone is a beta cut. That's how we are doing. I took the solution image also and we will compare it with that. This is from some of the weekly notes. See, we are cutting at proper places only or not. We are cutting one above D and we are cutting here. Okay, they have just kept on doing, putting all this 10, 10, 10, 10 here everywhere. I don't see that is helping because that is just creating a confusion. With taking appropriate numbers with us, we are able to prune properly. See here 10 is there, 10 is there, and it won't make me satisfied to cut here. Anyway, above J we are cutting, above L we are cutting, and above this we are cutting. This is the solution given in the weekly notes. So that's how we are arriving at this alpha beta cuts. These are alpha beta prunings, alpha beta cuts we identify based on this. So I think I'm clear. Shall we move ahead? Do we need to spend any more minutes on this? Sayan or Shawnee, Prashant, Sandeep, Shandeep.
That's all. We are completing. One more thing is there, no?
Yes, plus star is there. We'll finish that and we'll complete.
Yeah.
Yeah. Okay. So triple star also we have some mantras like this to by heart, and with that we will easily do that. Okay. So first of all, for triple star we need a cluster. A cluster is an opposite of strategy. At strategy, we are taking one choice for max and all choices for min. But for a cluster, it is an opposite. Take all choices at max, one choice at min. That is by default. Okay, so for triple star, identify initial cluster. How do we identify cluster? Take all choices at min, all choices at max, one at min, one at min. All choices at max, this is all choices at max, and at the end, one at min, one at colors are overlapping. No? Make it different color. Okay. All choices for max, one choice for min to extend. All choices for max, all choices for max, one for min. This is the initial cluster that a triple star forms. This whatever is highlighted in red. And the horizon nodes of the initial cluster are this A, C, I, K. These are the initial, right? Initial clusters horizon nodes. A, C, I, K. Okay, so what we do is basically we have two things to keep note of. One is solved. Okay, I'll put as C in order, and another is processed order. C in order, I'll put the numbers there. Processing order, I'll put here. In what order they'll process. Okay, out of all these clusters, we see one by one from left to right. We will see them and put numbers A, C, I, K. That is how I visit and I identify these nodes. A, C, I, K, I have identified in this order from left to right order. I want to explore all these nodes. So by default, the leaf nodes are always in solved state. So the processing order will be highest to lowest based on their values, highest to lowest. Because this is game theory and we want highest numbers, not like search or TSPs where we want minimum cost. So the processing order out of this ACIK, the first to choose is A, and C, and then K, and then I. I'll process in this order. A, C, I, and K. By default, A is in solid state. By default, C is also in solid state. I'll put a salt. Because these are leaf nodes, we know their values, so we are directly putting them as salt. And one more. Okay, I'll take the numbers also for ordering easy. C is 15, and K is having a value of 13, and I is having a value of 5. ACIK. So next, I'll pick one by one from here and I'll process them. First, I'll pick top node, that is A. Cut. For max nodes, what we need to do is, start with highest value horizon node. Okay, we have already starting. And if it is a max node and solved, we will check its siblings. If it is a min node and solved, we will prune its siblings. These two are the rules. Max is solved, we check siblings. Min is solved, we prune siblings. Okay, so first we took A and it is solved. This is a max and it is solved. Now what we do? We need to check its siblings. So we take B also into consideration. B is at visiting number 5. But we don't process it immediately because it has a value of 5. I'll put it in this order. B, I'll put it in live with 5 because I'm yet to do that. It is not a default node. I'll put with value 5. When its turn comes, I'll do that. I'll do the processing. Okay, go ahead. Next, I'll pick C. This is also a max node. When a max node is solved, you check its siblings. So I found D is with value 11. So this is my next scene. D is the next scene, and I will insert it with live, and its value is 11. For this, in this order, I will come. I don't, since that I saw D now, I want to go and work on it now itself. I'll come one by one. Okay, the next one is K, I'll pick K and I'll start working on it. Pick K. This is a max node. When a max node is seen, we'll consider its siblings. So K is 13. So till now the seen number is 6 and its sibling I want to see. So L, I have seen it 7th timestamps we can say, and its value is 12. So I will add it to the queue. Wait there, I'll explore you when the turn comes. Okay, light 12. So this is in the top of a queue. Think that this crossover is not there. Okay, I have added it to queue. Okay, then pick the top from the queue. L. Now I pick L. This one. This is a max node, so I will process it. So process it in the sense here I have 13, here I have 12. Process these two, and now I have a value of 12 here. What is the number of this node? 1, 2, 3, 4, 5, 6. So this is some D6. I have 12. I need
Ma'am,
to work on it.
can you repeat this one when you for the L?
Yeah, L we are processing. No, I added L to this queue. Now its turn has come. As per the order I have added, and now L's turn has come. So there are no more siblings, right? For K, there was a right sibling, so I added. For L, it is the rightmost sibling. There are no more siblings. So go ahead and give away the values. K is also closed. L is also, I am closing now. I am moving it to solved state now. Closing means I'm moving it to solid state. So once K is closed and L is also solved, what I can do is I can take only these two values upwards. No, that is meant by processing it. Once these two are processed, I take this value upwards. 1, 2, 3. This is B, C, D. No, 1, 2, 3, 4, 5, 6. Yeah. Now I have D6. This node. It has a value of 12. I won't process it or take it anymore. Now itself I add again to the queue. D6, it is live with a value of 12. You are yet to be seen. Okay, I added it to the queue. Since it is in the top, suppose here there are more numbers, I will come to it later. But here it is on the top, so its turn has come. Choose this, make it a salt. Okay, solved. This is a min node that I solved now. What should we do when a min is solved? We should prune its siblings. This is D6. This is its sibling. I'll prune the sibling. That's what we mean by solving a min node. When a min node is solved, I'll prune its siblings. When a max node like K is solved, I'll check its siblings. If siblings are there, I'll take them the queue. If no more siblings are there, I'll process that level and give away the values. Those two are the rules for triple star that we wrote. Okay, clear till now? So D6, when it is solved, it pruned its siblings and it gave away this value of 12 to the above guy. Now this guy is C3. Now it is his turn. He has got a value. He also need to go and sit in the queue. C3 with a value of 12. Now will sit. Now will sit as live in the queue. C3 12. Okay. Now whose turns to pick? C3 is the person I pick now. I am solving him. C3 is solving. This is a max node. For max node, when it is solved, what should we do? We should check its siblings. No? Yeah. We should add its siblings and a pruning problem. Where am I? 5 and 12 above. I have a pruned. Yes. So here I have pruned. Correct. Okay, C3. Now I need to check its siblings. So this guy is C4 and we will go all the down till M and I will take this. Take this M will be having number 8 because for checking there is nothing here. I need to go till here. This is okay. Got it. So checking means there is nothing here. Go till this level Yeah, this is the next one to add, because they don't have any values here, no, to add into the queue. I have only m to add into the queue. I see m next with a value of 13. Sorry, it gets added into the queue. M is live with value 13. Add it into the queue. Okay, then pick from the queue. It is m's turn only. I cut this. It is solved. M is a max node. When it is solved, I should take its sibling into account. So I visit n at number 9. Take n into this queue. N I take with live, its value is 14, I think. Yes, take here. Obviously, he's on the top position in the queue, so I will check also. Now, M and N both are done. They give away this value of 13 and 14 to this guy. He takes a value of 13. When I go and put him in the queue, obviously he's at the top of the queue. So let me proceed and prune his siblings. Min node, he is being solved now because he is in the top of the queue. I just did not write the queue anymore. Top of the queue, so I am pruning his siblings. Give away the value of 13 to parent. This is a max node, no more siblings to explore. So give away the value. This guy 12 and 13 will take a 12. I'll try to go and put him in the queue. He'll sit on the top of the queue. So immediately, wait, yes. So immediately I'll solve him. When min is solved, prune its siblings. The value here is 12. That's it that we have solved. We visited only these nodes. Let me compare it with, yes. So whatever is in gray, it is pruned. Also see the numbers. A, B, C, D got 1, 5, 2, 6. This is from the solution document. I got 3. KLMN got 4, 7, 8, 9. So we listed in correct approach and we pruned accordingly. Here we pruned, all this part of the tree has gone into gray color, but these nodes were part of initial clusters and initial explorations. So they were maintained somehow in blue, but we didn't explore them yet. Okay, they just got seen numbers. We didn't process them completely. Right, again we pruned here from this image, we pruned here, so there was a gray beneath that. 5 we went once, 12 we didn't touch, yes, and we found a pruning here, yes, we noticed a pruning here, the right branch we didn't touch. So we pruned appropriately. That's how we are doing. After some time, what happens is you need not write into this queue manually. You keep seeing 12 and 13, 14. You need 15 from 15. You need not write because that is always going to be on the top of the queue, and you do them whenever they come. That's how it is. It is going to be. This is the order in which the nodes are exploding to plus star. I hope I am clear. Naresh sir?
Nicely explained, ma'am. Thank you very
Yeah.
much.
Thank you. So that's it. Triple star. After this, I don't have any more much because I just put some what is that points about week 8 just to make it complete with respect to quiz 2 session. So for week 8, we were seeing that all the earlier algorithms were mostly with respect to states. Now we are moving towards planning. One is forward planning, where we identify initial state and we slowly we move towards the goal, and we find the actions. We make a plan. So many actions is possible, but the goal is small. We see a very huge tree, so we identify that this is a bad choice. And BSSP, we come in the wrong opposite direction. We start from goal, we take relevant actions, we keep adding, and we prepare a plan from this direction, from front only. So validity is a problem here. So maintaining these two, the GSP algorithm was designed. It was like searching from backwards but constructing plan from front. Push actions and pop goals or actions from the stack and push the relevant actions. I think this is simple from the practice assignment. I just put two images. If you want, we can slide that. We can do that, or shall we wind up here? There is one more topic called plan space planning, no? But I see that this is also all graph based. We see from the practice assignment that we can simply identify which link connects to where. So something like this. On BD we can connect to something. So yeah, some connections we can establish like this. This was easily doable from the graphs. Just for completeness, I have put them here. Yes. Shall we wind up our discussion? Sahil, Rakesh, Sujay, others.
Yeah, so everything was nicely explained, madam. Thank you very
Thank
much.
you, sir. Thank you. Thank you. Yeah. Yes.
Personally, for me, this TSP BNB, that speed or the correct way of doing in a faster method, no, that I am not able to still. I mean, after
Yeah, yeah.
listening to you a little bit, I
Many
got
was
idea.
yeah, yeah. Even in quiz one, I was also giving so much of time for these numbers calculations and DFS, BFS, and also I
I'm
lost marks
trying.
because of manual calculations only.
I'm trying different methods. One or two methods I tried,
Yeah,
and the
yeah.
third method
I'm
again.
also
I'm trying.
planning to do. I'm also planning to do the maths quicker this time at least, so as not to lose.
Okay, okay.
Yeah.
I'm using colors actually for each and every the after SO. I mean S0. You
Mm-hmm.
come down. I am using colors in the what do you call the grid.
Okay.
Which one we are removing, which one we are adding. Basically, more
Okay.
maximum you will get only three. Once you
Okay.
remove one edge, I mean that
I got
not
it.
BC, not AD, something
The
like that.
other edges become obvious, and we some it come.
And every time when you calculate, only two rows will get changed.
Yeah.
So other rows we can actually put the same number. So I'm putting like a matrix. A, B,
Right.
C, D, E will be there, or in all the questions they are asking up to six nodes. So A, B,
Okay.
C, D,
Okay.
F will be there. Then
Hmm.
you find two minimums in each row and calculate the lower bound. That is one particular one mark question will be there, lower bound. Then in that itself you find the lowest edge and
Hmm.
you add that if it is whatever edge is there, you bring down from S0, you come down with one more thing. The left side will always have the same values.
Yes. Yes. I got it.
And then not
Whatever.
BC means you go to B, you don't take BC, and you go to
Yes.
C,
Yes.
don't
I
take
got it.
BC. But
That depends again on individual's
this
approach and
one you add.
speed. Yeah.
So, so you feel what I'm trying to do is somewhat faster or something like that? I don't know. Lot
Yes.
of
I
working.
stopped streaming. I stopped streaming.
Yeah, yeah. Sorry, you're streaming. Okay.
No, I don't know, sir. It again depends on individual's comfort with
Yeah, that's why I asked
speed
you.
and numbers.
You're not still recording. You are still on record.
Yeah,
No
that's
problem.
okay.
Okay.
There's
This
nothing.
IITM recording or you're recording?
No, no, not from me. It is from Shamadeep. He gave me this link with this privileges. I
But
don't have.
it will be used by IITM if they wanted, no?
I
If
don't know. It
okay,
says some Gmail with some access provision to record. I don't know from where he got it. I don't know
okay.
where he streamed also. News
No
channel or
problem.
let. Oh
Mm,
no, this is Google Meet stream only.
yeah. Lalu Prasad, can you just throw some light on BNB TSP?
Hello, sir.
Laluji.
Myself.
Yeah, I'm just asking you. Have you completed BNB TSP?
No, still I didn't practice that.
Not
Like,
at practice. Okay, okay, no problem. And anybody else? Jacob, Sushil, Sahil, Sayan, Sujay. Okay, nobody. Week eight,
Hmm.
madam. Uh,
How will I? If I stop the recording, where will it save? Also, I don't know. I think Shamadeep left. He gave me host control and he left. If I
yeah,
stop
you can
recording now,
stop. recording, no? They would have recorded. Wherever it has gone, it would have recorded. I don't know.
Okay, organizers